Hi, my name is John, and this is my lab 4 on DC and RC circuits. So the first part is the introduction. The problem this lab investigates is first to predict the behavior of circuits containing resistors and capacitors, and second to measure the relevant data, including potential difference and time constant. I divided this lab into those 6 sections, and my final results are first. From the first experiment, current equals to 0.02A and voltage equals to 3 volt. And from the second experiment, the time constant equals to 5.95 seconds. Some of the key physics concepts involved here are first the NOT rule, which is the current in equals to current out. The loop rule, which is the sum of potential difference equals to 0. And Ohm's law, which is R equals to delta V over I. And in my first experiment, I connected 2 batteries with 2 resistors in series, and the current by using the Ohm's law should be delta V over R, which is 0.02A, and also my ammeter here read the same number. And the current when the ammeter are connected backwards should be negative 0.02A. And here I replace the ammeter with a voltmeter. And my current equals to 0, and my voltage equals to 3 volt because that's the voltage of the battery. And then I measure the potential differences on each section of the circuits. Here are my values. The current equals to 0.02A. As we can see here, the sum of the delta V is indeed equals to 0. And here's the graph I draw to show the changes of the potential differences. At the end, the potential difference goes to 0. Then I connect a ammeter in parallel with a resistor. As a result, both of my resistors read 0.06 A, which is 3 times larger than the first reading. This is because ammeter has almost 0 resistance, and our current will go from the ammeter rather than through the resistor. And that by calculation, we know that I equals to delta V over R, which is 0.06A, which is the same as my ammeter reading. My answer to this question is that voltmeter has a large resistance, so almost all the current will not go through the voltmeter, leaving the current value unchanged. And also recalculate the resistance value based on the potential difference value I measured and the current value I measured. We can see that those values are pretty similar. And the resistance of the wire is 0, and that's the same for my ammeter. And the second experiment involves a RC circuit. So when my capacitor is charging, the light goes dimmer and dimmer until it's fully stops shining. And my current also goes slower and slower, and then it fully stops. And that's the same thing for when my capacitor is discharging. The light goes dimmer and dimmer, and the current goes slower and slower. And the time it takes to charge for 10 ohm is 8.9 seconds, and for 20 ohm is 18.1 seconds. And the time it takes to discharge for 10 ohm light bulb is 8.7 seconds, and for 20 ohm bulb is 18.2 seconds. So we can see it's almost doubled when the resistance is doubled. Also, the charging time is kind of similar to the discharging time. And then I measure the time and also the ln of voltage over the initial voltage. And then I draw a graph to show their relationships. And the slope of the equation is negative 0.1668. And the RC is a negative reciprocal of that value, which is 5.95 seconds. And we know the theoretical value of RC is simply R times C, which is 6 seconds. So my measured value is pretty close to the theoretical value. And my answer to the first lab question is that current would be decreased since the actual ammeter has a small but non-zero resistance. And my answer to the second lab question is that the ideal model would predict a quicker time to charge. In real life, the wire still has a resistance, which makes the charging time slower. And as a conclusion, the data from my first experiment is in high accuracy, which involve those three values. The data from my second experiment contains some errors due to the timing by humans because time measure will be larger than the real value due to humans' reaction time. And my data from the second experiment involve those five values: the time constant and two charging time and two discharging time.